Okay, now almost there. Bingo. All right, now we're in business. So we're good? Yes? You can see all that? Excellent. Let me drag this over here. I am recording, so try to watch the swearing, Kaylee. Just saying, being proactive there. Okay, let's start with 52, because 52 is a classic example of the struggles that you probably ran into in this homework. Okay, so limit as delta, no, not delta x, as x approaches 3 of 3 minus x over x squared minus 9. Okay. What number did I say this was? 54? All right?
52.
52, thank you. Okay. So, if I gave you the problem if the problem was different, if the problem said this, would you know what to do? And if so, what would you do?
Factor it and then cancel out the x minus 3.
Love it. Whoopsh, whoopsh. Plug and chug, we're good. Okay. That's not what that says, though. So this is where we need to get a little bit sneaky. I'm going to rewrite this problem. Oh, yeah. Like that. Factored out a -1 out of the numerator. Then the rest falls into place, hopefully for you. -1 times x minus 3 over x minus 3 times it. So then it becomes a problem like we just finished over there on the right. Whoopsh, whoopsh. And we get -1/6. Okay? So the limit itself is not difficult. The algebra really isn't that difficult if you see the trick. If you don't see the trick, then we obviously have some problems. Okay? I had 62 next. But before we move on to 62, what happens, any problems with 54? I'm assuming if you plug and chug, you get 0 over 0. Can somebody confirm that?
Yeah.
Okay. So then factor the top, factor the bottom, and again, I'm assuming that something cancels and you plug and chug, yes? Okay, good. Simple problem. 62, however, all of a sudden some delta x's show up there. And I want to talk a little bit about that one then. So that's, let's go here, slide this up, change colors, that 60. Okay, I have a short attention span. What am I doing? 62. Okay, x plus delta x squared minus x squared over delta x. We're going to take the limit as delta x approaches 0. The right-hand side of that equation should look familiar. We've done this a couple of times. Yes? Okay, call that the difference quotient. Now what we've done is we've introduced this limit into the problem. You want to hold that limit until the very end of the problem. Unfortunately, you have to write the limit as delta x approaches 0 every time you simplify this. Okay, so x squared plus 2x delta x plus delta x squared minus x squared all over delta x. How am I doing so far? Have I lost anybody? Are we good to go? Give me a thumbs up if you're good to go. Beautiful. Canceling. Whoopsh, whoopsh. Okay, now what? Limit as delta x approaches 0. The top has a delta x in common. Going to factor that out. Cancel again. So now, what's the limit of this as delta x goes to 0? 2x. And we're done. Okay, so at that point, at the very end, I'm taking that limit, plugging 0 in for delta x, and I get my value. It doesn't always have to be a numerical value. It can be an equation like I have here. Okay, and if that caused some problems for people, I understand. Okay. Now, what does that mean graphically? We have no idea, and we don't want to go. This is probably one of the most important things we will talk about for quite some time. But we're not ready to talk about it yet. There's some serious relevance to that equation, which we don't care about right now. Okay. So if you don't get a numerical, we know from looking at graphs that we're expecting numerical values. What number are we getting close to? Now all of a sudden I'm taking a limit, and instead of getting a number, I'm getting an equation again. That's okay. Why that happens will be explained later. You just got to trust me on this one. Okay? Make sense? Is this helping? All right, let's talk about some of the other problems. Number 60. You can do that a couple different ways. What I would do is get rid of the fraction within a fraction. So I would multiply the top by 4 times x plus 4 and simplify that, then take the limit. Okay? Whenever possible, I'm going to get rid of fractions by multiplying by the denominator. Okay.
Mr. Reedy?
Yeah, go ahead.
I don't know if I missed this or not, but can we go over number 60?
Yeah.
Thank you.
You're welcome. You got to help me a little bit, Max. It's the limit as x approaches -4.
0.
Oh, even better. Of 1 over x plus 4 minus 1/4 all over x. Is that right?
Yeah.
Okay, beautiful.
Yeah.
Okay, so plug and chug. 1/4 minus 1/4 is 0 over 0. No good. Can't do it.
Yeah.
Step 2, algebraically manipulate. So that's what I was saying is I don't like this fraction within a fraction thing. So I would multiply the top by 4 times x plus 4 and multiply the bottom by 4 times x plus 4. There are other ways to do it. This is the way I like to do it. Okay? Now this seems ludicrous. Why would I do this? Well, first of all, I'm okay doing that because notice that that's equal to 1 and doesn't change the outcome. The reason I like to do this is because it eliminates all the fractions. So if I take this monster and I multiply it by this, it's going to give me 4. Yes, we're all good on that? Some algebra stuff here. If I take this whole thing and I multiply it by 1/4, it's going to give me x plus 4. Parentheses, very important. All over this whole mess on the bottom. Do not, under penalty of death, do not do this. That is silly. Why is that silly? Because there's a minus sign there. But you'd be amazed at how many people will do that. So don't do that. Simplify. The limit as x approaches 0 of 4 minus 4 is 0. We get a negative x on top. I'm going to leave the bottom alone for now. However, I do realize that I've got some more canceling going on there. That leaves a negative 1 on top. And then at this point, I'm hoping I can plug and chug. So what happens when I plug and chug? That x is gone. I get negative 1/16, I'm thinking. Okay. So again, moving forward, this is what I was talking about, these problems where you need the trick. So that's the trick that you're going to use in that problem in order to simplify it. I don't think the limit is difficult. I don't think the algebra is difficult, but just seeing that trick to get it to that point where you can work with it is the key. In 65 through 70, your goal is to algebraically manipulate those things so that you end up with one of the theorems we talked about. Whoops. What's that equal?
1.
1, very good. And the other one is the limit as x approaches 0 of 1 minus cosine of x over x. What's that equal?
0.
0. It is minus, right? Not plus?
Yeah.
Okay, good. All of those problems, the goal is to get one of these things in there because we know what they are. Okay. So for instance, if we look at 65, I can just move the 1/5 out in front because it doesn't matter. The sine of x, the limit of sine of x over x is 1, so we get 1/5 as an answer. That's an easy one. Something like 66, the 3 doesn't matter, so you get the 1 minus cosine over cosine. Going to get 0 there. Here we can split it into two parts. So let's talk about 67. 67. Whoops. The limit as x approaches 0 of the sine of x times 1 minus cosine x all over x squared. Now your first reaction might be, okay, I'm going to distribute the sine of x. Don't do that. What you really want to do now do you see where I'm going with that? This I know, it's right here. This I know, it's right here. 1 times 0, 0. Because remember, the limit of a product is the product of the limit. I apologize for those of you that go back and watch the video. When I'm using my pen on the board, it makes a lot of clicking noise, a thumping noise. There's nothing I can do to control that. I could use my finger, but then I can't write very well with that. Okay, how are we doing so far? Questions? Yet?
Mr. Reedy,
Yo.
can we go for 85 through 88?
Yeah, I'm getting there. I'm not done yet.
Okay.
I'm just dipping my toe in the pond right now, so I haven't jumped in yet. Who was? Bella, is that you?
Yeah.
Go.
I'm still a bit confused with the trig function ones. Could you go over like 70 maybe?
Sure. Tangent squared x over x. Okay, this is number 70. Limit as x approaches 0 of tangent squared x over... Was it over x? Yes? Thank you, Che. Okay. Again, even though we're getting into an ugly trig problem, the first thing you should do is plug and chug. Tangent of 0 is 0 over 0. Okay, that doesn't work. So we have to come up with something else. My immediate reaction would be to do the following. Turn the turn the tangent squared into a sine squared over cosine squared. Okay, then what? I'm winging this, by the way. Let's see. That is sine x over x times sine x over cosine squared x. Okay, do you see how I got to that step? dividing by a number is the same thing as multiplying by the reciprocal. So the work that I left out there is I actually did this first. Okay. So instead of dividing by x, I multiplied by 1 over x, which will end it up in the denominator. Then, from what we did earlier, I want to see if I can get this puppy into play, which I did by taking the sine squared and splitting it. Okay? Now, does that get us where we need to go? Well, I can take the limits then. I know that this has a limit of 1, according to the theorem. The sine of 0 is 0. The cosine of 0 is 1. Squared is 1, so this gives me 0. And 1 times 0 is 0. That's a lot of work to get to 0. Now, there's probably other sneakier, craftier ways to do it, but I just kind of took a brute force approach there and converted it to sine and cosine. Like, for instance, there's a trig identity that says tangent squared is 1 minus secant squared. I could have used that. But then I got to do a bunch of other work on the other end. So I think that's probably the best way to do it. Does that help, Bella?
Yeah, thank you.
The thing to remember about the trig functions is that you want to work towards those two identities somewhere along the line. Okay. Okay, so in 85, 86, and 88, this crazy little equation pops up again that I just talked about. It's like super important, but you don't really know at this stage why it's super important. So we're just going to pretend that we know why it's super important and move on from there. Okay. It's just like the different quotient we've done before. We're going to plug and chug. We're going to simplify, and then the last thing we're going to do is do a limit. So just for giggles, well, Christian, I'll ask you, do you have one in particular you'd like to do other than 85? Because 85 is almost a little too easy once you see how it's done. 86 or 88, do you prefer?
Let's go for 86.
86 it is, the square root of x. Okay. So 86 is f of x is equal to the square root of x. Okay, so I'm going to do the limit as delta x approaches 0 of f of x plus delta x, which would be the square root of x plus delta x, minus f of x, which is the square root of x, all over delta x. Okay, so that's the setup. That's plugging and chugging into the what's called the limit difference quotient. Okay, now what? Well, I have a limit. First thing I should do is plug and chug, and you see that you get 0 over 0. That's bad. So I have to algebraically manipulate. You're not going to like this. Any ideas how I would algebraically manipulate that puppy? Anybody? Any ideas? Right. If this one's ugly. This is probably I think the hardest problem on the homework.
Square it.
Can't. Now the reason you can't is because it's not an equation. Squaring would be okay if we had an equation as long as we squared both sides. But we just have an expression here that we need to simplify. But you're on the right track. To get rid of the square roots, I'm going to want to multiply it by another square root. So, your friend and mine... I'm sorry, what?
Rationalize it?
No, because there's no square root in the denominator. But it's kind of like a rationalizing. Do you know the word conjugate? Yeah, it's a little... Okay. So, the conjugate of this would be the square root of x plus delta x plus the square root of x. So, Christian, you happen to pick the nastier one. But that's okay. We'll get it done. Remember, this expression is equal to 1, so I'm okay. And now we just do the grunt work. and you just got to muscle through this. So multiplying a binomial. The reason you use the conjugate is one of the good things about it is the b term from a normal binomial product will drop out. So the square root of x plus delta x times the square root of x plus delta x is just x plus delta x. The b term disappears because one's minus, one's positive. Then negative square root of x times square root of x is minus x. And that's why we use the conjugate, because the numerator becomes nice and clean. The bottom is a train wreck, but I'm going to leave it as a train wreck because I don't want to make things worse. And that's a pretty normal operating procedure. Don't mess with the denominator. Okay. And so now, hopefully you see what's happening here. The negative x and the x cancel. The delta x and the delta x cancel, leaving a 1 up on top. And now I plug and chug. Okay, putting 0 for delta x, that goes away. Square root of x plus the square root of x will give me a final answer of 1 over 2 square roots of x. And that is nasty. So let's talk a little bit about, let me talk a little bit about, suppose this was a test question or a quiz question. What am I looking for? Well, first of all, I want to know, can you set up the problem correctly? Do you know what f of x plus delta x means? Did you remember to put a parentheses around that second one so that in case you have to distribute a minus sign? Okay. Step 2 is the algebra. Did you know how to simplify it? In a problem like this, I would not expect you without some guidance to come up with the conjugate. Then, did you simplify it adequately enough? And then the last little tidbit is, did you take the limit correctly? Did you put 0 in for delta x and get the correct answer? Okay?
Mr. Rudy,
Yo.
the answer key for 86 says 1 over 2 root 2.
Then that's a typo, because it shouldn't be 1 over 2 root 2.
Okay.
Okay. This, I'm sure this is correct. So I'll have to go and change that key. Okay. Lastly, I want to take a look at a sandwich problem. And only because I told you not to write it down, but then I gave you a homework problem. So I'm going to show you what it looks like when you build this sandwich like we talked about in the lesson. Okay, so we'll do 94, which is absolute value of x times cosine. All right, first of all, just for giggles, if you haven't already done so, graph that on your calculator so you understand what it looks like. Or on Desmos or on whatever it is you're using for your graphing excitement.
Sir,
Yo.
how do you get the absolute value sign on your calculator? I don't know how to do that.
Good question. The way I do it is, hold on, let me grab my calculator. Do you see above the 0 where it says catalog?
Yeah.
I go second 0, and the first thing that pops up there in the catalog is ABS, which is absolute value.
Oh.
That's how I do it. It's buried in a menu somewhere. I actually don't know where it is because that's how I get it all the time.
Okay, thank you.
Okay, no problem. Good question. So if I remember correctly, I think this is an oscillating function, yes? So do something interesting. Look at what you see on your calculator, then simply do zoom to enter. And it shouldn't look much different, right? And then if you do zoom to again, enter, you're just going to keep zooming in and it's going to look the same because even as you get very, very small values, it just continues to oscillate, which causes a problem, and that's why we need to do the sandwich theorem. Okay, so now you have an idea what it looks like, and the question is, how do we use the sandwich theorem to solve this? So we're going to build the sandwich. And we're going to start with something that we know, and that is the cosine of x is always between 1 and negative 1. Okay, so if you think of the graph of the cosine, it does this between 1 and negative 1. This center part doesn't match the function I'm looking for, so I'm going to make it look like the other function by multiplying by the absolute value of x. Which is okay as long as I multiply everything by the absolute value of x. So now I've built my sandwich. One piece of bread is the absolute value of x. The other piece of bread is the negative absolute value of x. And then the turkey, for a change of pace, is that ugliness that I don't want to deal with. I just want to work with the bread. From a graphical standpoint, what we just did is we said, okay, I've got this crazy oscillating function, but I managed to sandwich it between a nice little v up on top and a nice little v on the bottom. And then I've got this strangeness that's going if you just look at the graph, it's pretty easy to solve. The answer is 0. But the sandwich theorem allows us to justify it. So now I can forget about this and say, okay, what's the limit as x approaches 0 for the absolute value of x? And what's the limit as x approaches 0 of the opposite of the absolute value of x? In other words, we smashed our sandwich down, and both pieces of bread are approaching the same value of 0. So therefore, what do we know about the turkey? The turkey also goes to 0. Most of the time when you see a sandwich theorem problem, you're going to use trig because we have those relationships with trig. I use the sine relationship in the example, and then this one uses the cosine relationship. Because I'm a true professional, I finished that problem at exactly 10:30. Okay, it's taken years of practice. No new teacher is going to be able to do that. So I hope you guys appreciate the skill that I just demonstrated. Let's take 5 minutes. Okay, get up from your computer. Go do something. Go outside for 4 minutes or 5 minutes. It's beautiful outside. But get up. Do something other than sit at your computer. Go get a snack. Go get a drink. Okay, we're gonna do show and tell when you get back. I want to hear what you did. Go play in traffic. Okay, go chase a car. I'll see you in 5 minutes. Timer starting now. Up in above that TV, I put an X on it. There's a little red X up there.
That's concrete, right?
Yeah, it's the masonry.
It's one little one. I don't have to really the right bit for that. See,
It's fine. There's no rush though. I'm just saying if you're running around and you want something to do other than the BS they got, the hoops they got you jumping through. Yeah, I know. It's ridiculous, isn't it?
it's like, I don't know, there's like very little kids here. It's like,
Can you imagine if kids were here, how fun this place would be?
it'd be great.
Yeah.
Nothing is running. Nothing. Just they're looking at it.
I mean, if I understand things correctly, the contractors pretty much screwed themselves over, right? They just didn't do a job.
I don't want to get in trouble. But they
Sure, of course.
They fucked up. They fucked up. They cut the wire that runs the whole building. It's like, oh,
No kidding, really? Oh, of course. Who would I repeat it to, but
yeah.
they,
That's what we gotta. That's why nothing is running right. The controller that runs the whole school.
oh my God. done. That's good.
Well, it's awesome, man.
And then the shit runs downhill, and you guys
Yeah,
have
then
to, you
you-
guys have to fix all the crap.
Well, then too, they take the sealant, they throw them all out. It's like, dude, we're
These
missing
aren't
10
cheap, right?
6 of them, it's $100.
Really?
Oh yeah, they're $100 for 6 of them. Each classroom had.
I had no idea. I would have guessed, if you asked me what those cost, I would have said $5 a piece,
Oh, no,
which
no.
isn't cheap.
They're expensive. They're at least 10 to 15 each. And then, I would say on the average, every classroom, 8, 10, every classroom that had construction. It's like, are you kidding me? It's like,
It's almost so humorous that if you didn't laugh about it,
You
you would
laugh.
cry. I mean,
No.
it's ridiculous.
and George is a good guy, but go ahead. I'm on the 3rd floor right now. What's wrong with 226?
Same as 124. Too cold.
No problem, I'll head back down and I'll shut off the unit.
Go do what you gotta do. It's fine. It's no rush.
No problem. No, we can't even control the units.
You guys aren't working this weekend, are you?
Oh, no more overtime.
Good. And you have Monday off.
Well, yeah, I don't want to
Good.
work overtime anyway.
Yeah.
George is like, why don't you ever ask me for overtime? Because I don't want it.
Yeah.
I go, I don't want it. I go, if you ask me, that means you need me, then I'll come in.
Different story.
But I'm not gonna ask for overtime. I'm 59 years old.
Yeah.
If I need overtime now, I'm doing something
I'm
wrong.
the same way. They come and ask me, hey, do you want to sub for a class? I'm like, no.
No.
Yeah, but
Yeah.
there is no but. I don't need to sit. I don't need
Never
the-
mind. Don't worry about it.
I don't need the, I don't need the extra money. I'm okay, and I don't want to deal with the hassle.
10-4. I know.
I'm right there with you.
No, I don't want it.
Yeah.
And it's like my wife, why don't you do more side work? I go, because I don't want to. I do enough.
Yep.
That's it.
100%. I've been professionally painting since I was like 15. And so I paid my way through college professionally painting. I worked for a guy for many years. And so I do it on the side for like family and stuff.
Right.
And my wife is the same way. She goes, well, you could pick up a couple more jobs. I'm like, no. Because number one, I don't want to physically do it anymore. Like, I don't understand how you guys do this job. My knees would be shot, my back would be fried.
Me, it's my hands. My hands are all.
See, my hands are never a problem, but my knees, like, I'm doing a painting job for my sister-in-law. And I've been there like 3 or 4 weekends. And, I'm trying to explain to my wife, look, I'm working my ass off in this scenario. And then I'm going to get up Saturday morning at 7 o'clock and go paint all day? It doesn't work.
Painting is hard.
Oh, it sucks.
I hate painting.
It sucks.
I hate painting.
I don't mind painting, but it's physically demanding work. On the floor, painting baseboards and that kind of shit. And so I'm the same way with, like, I don't need this. I don't need this. I should be sitting on my porch. On
that's
my
all
deck
we do
having
today.
lunch. What's that?
That's what I'm gonna do. My wife is like, I'm gonna get stuff for the fire pits, the s'mores and stuff. I go, thanks for letting me know. I'm gonna stop and get the beer, and I'm gonna stop and get my cigars.
Done. That's all we're doing all weekend is we're seeing family. The kids are coming in town. We're just gonna, the hardest thing I'm doing all weekend is I'm making pulled pork. That's it. Everything else is sitting around with my feet up and drinking a
You
beer.
know what? Do me a favor. Just put a tape where you want to screw an anchor,
Beautiful.
and then if I had it, I would do it right now.
No, it's no problem, Phil.
Okay.
Thanks, man.
You want the door open or closed?
Close, please. Have a great weekend.
Bye-bye.
All right, we all back? Beautiful. Okay, let's jump to a quick talk about continuity. So the split that we had with limits versus continuity, I did the same thing with tonight's homework. So yesterday or the other day, I assigned some continuity problems, and then you'll do more continuity problems tonight and also a little bit of practice on the stuff that we're going to talk about in a little bit, which is really easy. Okay, so sometimes people get confused between limit problems and continuity problems. Okay? And they are related, but they are also very different. And I'm going to keep hyping on this formal definition of continuity. And I'm telling you, our next quiz is loaded with formal definition of continuity. So you have to have those 3 things burned into your brain. Okay. Find the funky point, and then once you find the funky point, is the function defined? Does it have a limit? And do those two values work? Okay, so let's take something simple like problem number 4. If I look at problem number 4, where's the funky point?
Is it at -3, 4?
Beautiful. It's at -3. Let's just generalize in the x value. It's something funky is happening at -3. Okay. The rest of it we don't care about. It's a straight line. We know it's going to work. It's continuous. I can pick it up with my pencil, or I can draw with my pencil without picking it up. Okay, so if we go through the 3 steps for number 4, is there a value of the function at -3? Okay. Now, the fancy way to say that is, hold on, let me get this straightened away here. Number 1, is f of -3, is there a value there? And if so, what is it? Four. Yeah, don't overthink it. It's just 4. And also, don't be bashful. I like some communication here. What's the limit as x approaches -3? 3. Very good. 1 and 2 are good. There's a value of the function. It has a limit. The problem is, part 3, 1 doesn't equal 2. The values are different. Obviously, 4 doesn't equal 3. Boom, discontinuous. I hope at this stage you could just look at that picture and realize those are discontinuous. That's a discontinuous function. Okay, I can't draw that without picking up my pencil. But there's also a technical mathematic or a calculus-based answer to that question that you have to be prepared to answer using that quote-unquote formal definition. Okay. By the way, in number 4, what kind of discontinuity is that?
Jump.
Nope. Correct. It's a removable, also known as a hole. 6 is a jump. Okay. I understand why you said jump because there's a dot there, but don't be tricked by that dot. It's still just a hole removed from the graph. Okay. I had 10 marked as one to talk about, but I already talked about it in the limit stuff. So I'm assuming you can figure that one out there. Okay. Again, do your factoring, plug and chug. You're good to go. 14 is probably easiest to do thinking about the graph. This is our mother function of the absolute value of x over x, shifted 10 units to the right. Problem number 18. We have a piecewise function now. That piecewise function changes at 2. However, it's also asking you what the limit at 2 is. And that piecewise function is going to do one of 2 things. You've got some function coming in from the left, and you've got some function coming in from the right. So at 2, they're either going to meet, which is good to go, we've got a limit here, or they're going to be like this. And you have to figure out which one it is. Well, how do you do that? You take 2 and plug it into the top, take 2 and plug it into the bottom. If the numbers match, we're good to go. If they don't, then we have a jump discontinuity and no limit. Okay, remember, left hand limit has to match right hand limit. (27) and 28, they gave you pictures. I think that's kind of a cop-out, but you can still look at the pictures and see. Again, using the KISS method, if you approach this and say, okay, can I draw 27 without picking up my pencil? Obviously the answer is no. So then what makes it discontinuous? And you go back to the 3 steps. The same is true with 28. 28, we have a hole, and we've talked about that like problem number 4 we just finished. Okay? Questions on the discontinuity. I'm guessing you found the discontinuity easier than those nasty limit problems we went over. Is that an accurate statement? All right, beautiful. Any other questions? Beautiful. Okay, let's put this. Marcus, go ahead.
Could you go over 16?
Ooh, yeah.
Oh, well, yeah, that's a big one, actually.
Well,
Just
it's actually pretty straightforward.
Yeah, maybe.
All you got to do, I say all you got to do, but what you should do is just multiply that puppy out.
Okay.
And a bunch of stuff is going to cancel. Do the canceling, and then what's left is a plug and chug. So it's comparable to the ones we did in the limit stuff too. Does that help, or you want me to grind it out?
No, I think that helps.
All right.
I'll just multiply it out. Okay.
Cool. Okay. All right, give me a second here. Let me get organized.